Hey everybody, welcome to Physics 151. This is an unusual way to start here, but I thought we could get a little leg up on some of the introductory stuff that you probably have some familiarity with, um, especially since we won't be having class next Monday. So this first lecture is just set up as a kind of list of physics problem solving tips as a way to introduce us to some good basic science that I think we need to be reminded of every now and again. So the first problem solving tip is to pay attention to your units. Uh, the fancy word for this is dimensional homogeneity, um, which is harder to say and understand than pay attention to your units. So here we are, just a little fake problem here. Let's say we wanted to find the density of a combined fluid and we knew the mass of one of the fluids and the density of the other. Density is then mass over volume, which you can see by this unit here, right? So how do we combine these things? Well, clearly we can't just do this, right? That doesn't make any sense. And we know that. We see this, and this should look really weird to us, right? We should have, with more and more practice, that looks stranger and stranger. And so we're not allowed to do that, right? So what's the rule here? Well, any equation that we're joining by one of these terms, plus, minus, greater than, equal, has to have the same units, right? We can't add things that aren't alike. If you want to find out how many, um, I'm going to pass on the example that just popped into my head. So anytime we see these, we have to make sure that the things that are being added are the same, and then our units over here have to be the same because we've got this equal sign. The more technical way of talking about this is to look at what's called the MLT system or the FLT. This is mass length time. This is force length or mass length temperature, force length temperature. Um, but we can make a fascinating observation, and this is sort of interesting. All of these different physical quantities, every physical quantity that we talk about in physics, we can describe using a combination of mass, uh, length, time, and temperature. Um, it is mass, length, time. I'm sorry about that. I got my T's mixed up there. The big T is time. And so you can define any of these, take, we don't even have to know what something is. What's our modulus of elasticity? It's going to be m, a mass, over a length, and over time squared. Okay, something that we're more familiar with, something like miles per hour, right? We know that that is going to be length, miles per hour. Time is going to be length over time, LT to the negative 1. Okay, so we can take any equation and break it down into these MLT terms. We won't mess with the FLT terms. FLT is just another way of doing this. F, force, becomes a combination of MLT, and so you can use the same, you can use force instead of mass and then just divide by the necessary L and T's to get um, a correct equation. So let's go back to our equation here. We remember had mass over volume. Volume is length cubed. So this is density, ml to the negative third. It can look like this, ml over L to the third, or it can look like this, kilograms over meter cubed, or if we want to go to the British system, and whoever wants to go to the British system, we can go slugs over foot to the third. Those are all the same units here. They are all equivalent. Okay, and so then we can kind of see how this works in practice. If we want to try and convert mass to density, as we want to do in the problem we described, we can take density here and multiply it by volume. Those volumes cancel, and we get mass here. In the MLT system, this looks like this. ml to the negative third times L to the third, right? Length to the third is volume. These two are going to cancel out. gives us ml to the 0. L to the 0 is 1, right? Any number with the exponent 0 is 1. And so we end up with a mass unit. So let's test this out in a way that we might actually use. Like say that we went through a long algebraic equation and we ended up with something like this nasty looking equation that we have here, which is mass times g times h equals half times mass times v squared. Looking at this, you can't really tell whether that's dimensionally homogeneous. And so we have to do a little bit of work to figure that out. So each of these terms, some of these we don't know these terms, like g or I here. And so down here it tells us what the units of those terms are. For instance, g, which is the gravitational acceleration caused by gravity, has units of L(t to the negative 2), and in metric units, that's meters per second squared. Okay. Velocity has units of L(t to the negative 1), and in metric units, that's meters over second, just like meters per second or miles per hour. So let's check to see if each of these three terms are dimensionally homogeneous. Why do we call it three terms? Because they're separated by either an equal sign or a plus minus sign, or less frequently a greater than or less than sign. If they're separated by that, then they have to be dimensionally homogeneous with each other. So let's check here. So our first term is mass times gh. So our mass term is kilograms. Our g, if we go down here, is meters per second squared. And then h is meters. That's height. Okay, so that's kilogram times meter on the numerator in the top. Kilogram times meter squared over second squared on the bottom. So there are our units. Not a term we're familiar with, right? As it happens, this is actually the units for energy, which we'll get to in the course of the class. Let's check our second term, mv squared. We've got kilograms mass times v squared. So here, the square term has to be outside of here because our v is meters per second, and we're going to square all parts of it. Okay, so we get meters squared over second squared times kilograms. Hey, looks the same, right? Works out. So those first two terms are dimensionally homogeneous. And then we check the last one. Kilograms, I here, which is the moment of inertia, is kilograms times meter squared, times omega squared, 1 over s, which we can find down here, squared. So here we have on the top, kilogram over meter times meter squared. On the bottom, a second squared. And they all match up. So happy days. We didn't make any dimensional mistakes in our algebra. That doesn't mean the equation is correct. It just means that that part of it, the units of it, are correct. And at least we know we haven't made a major error. All right. So question or problem solving tip number 2 is conversions. Something people have trouble with fairly regularly, right? Oops. I'm trying to figure out my highlighter here. If we go back to this problem and now, okay, we know it's 3 kilograms. Now we know what the volume is, okay? But we want to we have one that's in kilograms per meter cubed. We have one that's in kilograms per centimeter cubed, right? So how do we solve that, right? A lot of times I think students will just sort of try to do this in their head, and I want you to encourage you to instead go through the process of converting these types of equations. So how do we do that? We multiply things by unity. And in order to multiply by unity, you multiply by a value that is equal to 1. Okay, so 100 centimeters is the same as 1 meter. So this is just 1. This is 1. Okay, And so what we're doing here is we want to get rid of 3 centimeters on the bottom and replace it with 3 meters on the bottom. So we've got, if we cancel out units here, we've got centimeter cubed on the top, centimeter cubed on the bottom. And that means we need to multiply this number by 100, by 100, and by 100. And our units cancel out to give us kilograms per meter cubed. So then we can safely add these two values and take the average of them. And that would give us the density of that combined fluid. Okay, so you all know this, that you need to convert a lot, and I'm just encouraging you to use this sort of equation. Go ahead and write it out. Take the 3 more seconds to do that, and you won't make nearly as many conversion problems.